Hi there, everyone. Good to see you. My name's Lucian Wishick, and I'm a program manager on the VB C# language team. Today I'm going to be talking about Async, about language support for async APIs. This is the major feature that we shipped in Visual Studio 2012 for VB C#. Actually, we shipped it in VS 2010 for F#. I don't know how many of you are using F#, but you should all have a look at it. Anyway, a major new feature, and it's really important, right? It's important enough that in this conference we're dedicating 3 sessions on it. Today is the introductory async, just getting to grips with the concept. Tomorrow is the tips and tricks for using async, like if you've been using it for 1 week, what are the common pitfalls? And on Thursday I'll be talking about more advanced stuff, how to write libraries using the async language feature. It's very important. Actually, it's not just important for us. Let me set the stage. Asynchronous APIs are a trend that has been happening generally in the industry. There were faint glimmers in the mid-90s. It became more common, especially with JavaScript using Ajax. And now with Windows 8, most of the Windows 8 APIs are asynchronous. At the same time as Windows 8 was moving its APIs into this new asynchronous form, we in the languages team were trying to figure out, actually we were doing it quite independently. We recognized in the industry that so many different places were introducing this new style of API that it was inhumane for people to program with. And we set about creating a language feature that would make it humane. That's what this is going to be. So with our work on the languages side and with Windows 8 making all of their APIs different, the two forces with Microsoft aligned into a perfect storm. And that's what we'll be talking about. Gee, I didn't know you could do this with PowerPoint. Clicking won't make it come any faster. There's a saying by Leslie Lamport. He's one of the godfathers of computer science. He says, a distributed system is one in which your presentation can fail because a machine across the world that you've never even heard of has crashed. This one hasn't failed. I did this deliberately. But it's that spinning circle, that spinning toilet bowl of death, we sometimes call it, that is what async is combating on the client side. Think of, right, from the Windows 8 perspective or the Windows Phone perspective, imagine if you're using a tablet, you're swiping and touching and tapping, or a phone, and suddenly an end consumer gets one of those circles. They might have been partway acceptable on the desktop, but they're completely unacceptable for modern consumer devices. So it's clear that something had to be done. And Windows bet big on asynchronous APIs as a way of forcing programmers into coding patterns that would avoid those spinning circles. The other big push that we had was for cloud scalability, right? Say you're scaling into Azure or elsewhere in the cloud, and what you're looking there for is scalability and cost effectiveness. You want to fit as many users on each node of your cloud compute as possible, and that means you have to avoid wasting resources. And turns out one of the resources that you've got to avoid wasting is threads. And asynchronous APIs are one of the important techniques to avoid wasting threads on servers to achieve higher ASP.NET throughput, or higher any kind of web throughput in general. So, responsiveness on the client, scalability on the server, these are why people began to use asynchronous APIs, and in industry it's becoming the norm. So, what does an asynchronous API mean? It means I invoke an API, and even though it might be kicking off a long-running operation like retrieving file from disk or downloading off the internet or accessing database, I kick it off, but then it returns to me immediately. And what it returns to me is a future object. So it's not blocking my thread, it's returning immediately, and it's giving me a future object. And what this future object means is something that I can continue with off of it. I can sign up an event, or I can sign up a Lambda, or I can sign up some piece of work to be executed when that long-running operation eventually finishes. On the client, meanwhile, we're staying responsive. On the server, meanwhile, we're not wasting threads, just sitting there twiddling our thumbs waiting for it. So a future, previously in .NET, and everywhere actually, JavaScript, people were using ad hoc patterns to represent this. They weren't using, they were just saying, okay, you could sign up an event here, or you could pass a Lambda here, and everyone came up with their own ad hoc way for the user to signal what piece of work they want to be done. But now the industry is really crystallizing around future as an abstract concept. A future is a first-class object which represents an ongoing operation. When I say first-class object, I mean it's an object that's been allocated. It sits there in memory. You can dot off of it and invoke methods on it. You might have seen the task type in .NET 4, and we're borrowing that task type for our modern future object in .NET. At the same time, the Windows runtime has come up with its own infrastructure, its own future object. And the two, although they could have been different, we did a fair bit of work to bring them quite close together. There are still a few differences, but you'll see as I go through this talk that there aren't many of them. Let's just get on the same page about what we mean by the word asynchronous, because I think there are so many different opinions on what it means. Some of you might say, well, asynchronos, it comes from the Greek. A meaning not, syn, the same, chronos, time, not at the same time. Those of you who don't start from the Greek, I want you to think about it like this. Let's start by comparison to a synchronous operation up there. var data equals download data. And then we process it. So what that means is we have a small blip of work at the beginning, kick off. If it's download data, probably it's doing like 5 microseconds to initiate a web request to send a 512-byte packet across the internet. Then the packet travels across the Atlantic on fiber optic cable, limited by the speed of light, goes to a web server at the far end, limited by their speed of their database, whatever, comes all the way back, maybe 2 seconds. I think about, 50 milliseconds is the absolute fastest time we can get, given the speed of light across the Atlantic, but often longer than that. And we're just sitting there, twiddling our thumbs, until eventually the packet finally arrives, and we can do a small amount to process it. So that's the old synchronous case. The asynchronous case looks like this. We kick off a small amount of work, we get back a future object immediately, and control is returned back to us, so then we're free. We're free. These green dots represent taps or clicks or other UI events. We're free to respond to UI events. We're no longer displaying that spinning toilet bowl. Maybe 5 seconds later, the data comes back, and the stuff that we continued with, in this case, we signed up a Lambda to say, I want this Lambda to be executed once the long-running operation is finished. Eventually it finishes, and our Lambda gets triggered. As you can see in the synchronous case, if there were any UI events, like you're clicking it, why isn't it doing anything? I'll try clicking it again. Still not working. I'll click on the title bar and try dragging the window. Still not working. All of those got sort of pushed along until after the download had finished. Obviously an unacceptable experience for a responsive client app. And it gets worse. What if we were making 2 requests, one after the other? Well, we're twiddling our thumbs for 5 seconds in the synchronous case before we can even kick off the second request, which is crazy, quite frankly. In the asynchronous way of doing it, we could do it much better. We could kick off one request, get back control immediately, kick back a second request, then we're free to handle our user interface things, and whenever the things get ready, they come back. Maybe the second one finishes before the first, but then I can just handle it with my Lambda. So we look at this and we think, well, if we already have this handled with this continuous method or onCompleted event handler, why are we doing anything? And the answer is, lambdas are terrible and continuous is terrible, profoundly terrible. The reason that they're terrible is because they've completely broken up the flow of control in my normal code. Let's think. Computer science classes, they teach us the word compositional. They say, what does it mean for a language feature to be compositional? Well, let's think about the most rudimentary part of the C# language. By the way, I'm talking all this talk in C#. I should say exactly the same feature works exactly the same way for VB as well, but I stuck to C# for simplicity. What's the simplest part of the C# language? Probably the semicolon is the most basic building block for making one thing happen after another. Here, if we wanted process data to happen after download data async, we haven't been able to use the semicolon anymore, have we? We've been forced to use nested lambda. What if I wanted to do one download, and when it had finished, I analyzed it and kicked off another download? If I was using lambdas, I'd have to create a lambda and then a nested lambda within it. So instead of having a nice straightforward sequence of semicolons in my code, I've now got nested lambdas. If I try to extend it to a while loop or a for each loop or a try finally block, forget it. It's just, I mean, theoretically it's possible, but I've never been able to write it correctly. I've heard the phrase, you've heard the phrase spaghetti code, right? For go-tos, meaning control flow flows everywhere. I've heard someone call this style of programming with the lambda continuations, they call it macaroni code, because they said there are just these tiny nuggets of functionality spread amidst a big bolognese sauce of boilerplate code that none of us want and none of us can actually code review or audit properly. So, major new feature in Visual Studio 2012 is language support to let you invoke asynchronous APIs, but without having to use callbacks in your code. That's what's important about it. I'm going to go to a demo. Let's switch to the demo. The demo I wanted to pick is this mosaic builder. Mosaic meaning I want to have one larger picture built up with myriad tiny smaller pictures so that they look like a convincing whole. So in this application, I'll say, okay, I want to make something up of loads of different pictures of flowers. I'm going to go to Flickr and fetch 100 different images of flowers, of images that have a tag called flower in them. And I'm going to pick one of my images. Actually, I won't go to SkyDrive because I know what connecting to a network resource does when you're giving a talk. Let's connect to a local picture. Okay, it downloaded images off Flickr. Now it's calculating how can I fit those images into here. Took maybe 10 seconds, and it did it. It made up the picture out of lots of tiny things. Actually, what I wanted to show you is that while I was selecting it, the UI was still perfectly responsive. I could drag, I could swipe, I could hover. All of it worked correctly. So let's look at the source code for this. It's really a pretty straightforward piece of code that I want to show you here. If you've seen XAML, a lot of it will be familiar. Starting with the item click handler to respond when the user selects what they want their mosaic to come out of. Straightforward XAML data binding things, figure out which was the click to item, data binding it to the XAML so that things will appear correctly. Model.status text, that's data bound to a text block somewhere in the code. And then var picker equals new file open picker. If I hover over it, I see the type I'm getting back, windows.storage.pickers.fileOpenPicker. So I know that it's Windows namespace, means it's part of the Windows runtime. And picker, that means it's a Windows picker. That means it takes a full screen user interface to let the user select something or other. And with the Windows 8 integration into .NET, we can use the standard things like .NET Object initializers on them, just as normal. The next line is where it starts to get interesting. Picker.pick single file async. This is the thing that's going to cause the full screen picker to be displayed on the screen. Let's hover over it. Pick single file async. We see this is special. It's a special kind of method, an asynchronous method, an asynchronous API. How do I know that? Well, there are a whole bunch of clues. First, its name ends in the word async, and throughout .NET and Windows, all of the asynchronous APIs, with a few exceptions, end in the name async. Second clue is that the tooltip here says awaitable right as the very first thing, and its suggested usage is await pick single file async. So that tells me that it's going to be this special future type that I can do something with. And the third clue is that it's returning this type iAsync operation of storage file. iAsync operation is the Windows runtime future. Actually, it has two of them. It's also got iAsync action for futures that don't return any value. But here we've got an iAsync operation. I'm using the new await keyword, and it returned to me an iAsync operation of storage file. If I await it, I'm going to get back just the storage file. So it's going to unpack that future in some way. It's going to pop out just the storage file. So what does await mean? Well, the most important thing, and if you remember the earlier slide, the most important thing about calling an asynchronous API is that you get control back to you immediately. In this case, I want to get control back to the message pump, the XAML message loop that invoked my item click event handler in the first place. So the first thing that this await keyword is going to have to do is it's going to have to return back to its caller straight away. But before that, it's going to do the magic. It's going to figure out what is the remainder of this method. All of this remainder, it is under the hoods as plumbing for you, going to package away inside a continuation. So it's calling the API. It gives back an iAsync operation, and then it's going to call iAsync operation.continue with the rest of the method, and it's going to return back to its caller. It did that for you all under the hood. So you didn't have to worry about continue with, and you didn't have to worry about lambdas. All of it happens for you. The thing that enables that magic to happen is this async modifier up here. The async modifier tells the compiler, look, this method's going to be special. I want you to spit out plumbing code for the method to enable me to use await inside the method. The async modifier doesn't mean anything else. It doesn't mean run me on a background thread. There are no background threads involved here. All that the async modifier means is allow me to use awaits inside the method. Allow me to use awaits. Well, what happens next? Maybe 10 seconds later, I finished picking an operation. That meant that the file picker completed. That meant that the async operation knew that it was completed, so it executed whatever anyone had signed up for after it, and the await keyword had signed up the rest of the method, so it's going to start executing the rest of this method after I clicked the picker. First thing it does is this original file.openAsync, another Windows runtime API. Again, it ends in the word async. Hey, it's going to be an asynchronous API, and it returns an iAsync operation. And so once again, I'm going to await it. And if I await it, well, this was an iAsync operation of random access stream. So if I await it, I'm going to get back an iRandom access stream. So the await operator always unpacks what we had. There's one other interesting piece of code here. I can use await anywhere that an expression is expected. In this case, I used it inside a using block. That's one of the beautiful features of C# and VB await operator. Actually, one Windows 8 tip, I see a lot of people writing this code, but they forget the using statement. What does that mean? It means that their code normally works, but then they start to implement more functionality. They implement a delete button in their code. The user hits delete. It says, error, file cannot be deleted. Why can't it be deleted? Because they didn't dispose of the open async that they invoked. So I see a lot of people forget to use using on their Windows runtime APIs. A habit I just recommend to get into is when you use a Windows runtime API for the first time that you've never used before, try sticking a using in front of it. See if it works. If it works, then you're meant to use using on it. If it doesn't work, if it says this does not support using, then you weren't meant to use using on it. Simple as that. Anyway, where have we got to? Well, we're going to do straightforward XAML stuff. We're going to bind. Remember, the top image showed the picture that I've selected. So we're going to set that as the image. Actually, you can see here I'm using await not as an expression, but just as a statement. I can use await anywhere that statements or expressions would be expected. Later on, get Flickr URI. This is an API that I wrote as part of my application. You can see, even though it's an asynchronous method, I can still call my normal synchronous methods inside it. It's all the same. Next line, http client.getAsync. You see the async word. This is going to be another asynchronous API. But http client.getAsync API, it's not a Windows runtime API. This is a .NET API. HTTP client is the new .NET type we introduced in .NET 4.5 for doing web requests and stuff like that. It supersedes, it's better than the old web client, than the old HTTP web request. So you should generally be moving over towards HTTP client nowadays. What it's returning is not iAsync operation. Remember, that was a future type that belonged to the Windows runtime. Instead, it's returning a task of HTTP response. Task is the .NET future type. But even though it's the .NET future type, we can await it in exactly the same way with the await keyword and get back an HTTP response, unpacking the task type. What next? Read a string async. Pass photos from XML async, just processing that I need to do it. Fetch images async. Again, async, you know that it's going to be an async operation. You know that you're going to have to use the await keyword on it. What's interesting here is that fetch images async is not built in. It's not part of the Windows runtime, not part of the .NET framework. This API is an async API that I myself wrote. And what's great is that I can use the await operator anywhere. Windows runtime, .NET asynchronous APIs, or my own async APIs, or third-party asynchronous APIs. Use them all. There's no difference. The await keyword works identically on all of them. What I'd really like to draw your attention to with this is that I've really written my code exactly how I want to. Sequential block of things, one after the other, using semicolons. I'm not using lambdas. I'm not using nested lambdas. I didn't have to struggle writing the 50 lines of code needed to put callbacks to accommodate a using block. It was all very, very simplistic. Actually, when I say I could just do one thing after another, I probably did too many things after another. Let's refactor it out. I'm just going to refactor this chunk of code out. I'm going to do this to show you how to write your own asynchronous APIs. The reason I know that when I factor this out, it's going to be an asynchronous API is because it's got a whole bunch of await operators inside it. So let's do right-click, refactor, extract method. I hope you can read it at the back there. We can see that the extract method refactoring is aware of asynchrony. It knows that there were awaits in it, so it knows it's going to have a task returning asynchronous method with the async modifier on it. What it failed to do is give me the async suffix, which we should always have. That's a .NET naming convention, and I'm going to call it choose image async. Okay. And there, it's done it. Figured out what it had to pass in. Choose image async. It stuck the await operator in there, and it gave me back original file, just like I wanted. Let's go to dev to look inside to see how it's done. Choose image async. So, the marks of an async method is that its name ends in async as per .NET guidelines. It has the async modifier on it, and it returns a future type. For all of the async methods I write, it has to return task or task of T or void. It can't return an async operation. That's just a language restriction, but it's not a particularly serious one. And what it's returning is this future. Returning a future, just to recap, it means I want this method to return very promptly, and I want it to return the future immediately. Only later, when the long-running operation is finished, will the future be marked as completed. So let's step through what happens. Well, when someone invokes this API, it executes the first line, and the next line, and the next line. That might sound obvious, but it's not. And indeed, F# doesn't behave the same way. But it's executing all of the method up until it gets to the first await operator inside this method. The first await operator, it takes that as its signal that it has to return the future object to its caller. This is the time that it returns the future object to its caller. Actually, let me say that more precisely. The first await it gets to where the thing has not already finished by the time it gets to do await on it. Like, if I did await something that finished really quickly, finished so quickly that it finished before I even executed the await operator, then it would keep just plowing through the method. But in this case, pick single file async, it popped up the full screen. That sure as heck is going to take at least 5 milliseconds. The user can't click that quickly. So this is going to take time. It won't be completed immediately. So at the first await, it's going to return to its caller. And the return type is this future object, task of storage file. So somewhere under the hood, because thanks to this async modifier, the compiler is generating all of the boilerplate code needed to generate the future object and return it at exactly this minute. And, as we said before, sign up the rest of the method as the continuation to be executed when this thing finishes. Maybe 10 seconds later, the user clicks the file picker. They've chosen an image. At that time, the rest of this method gets to run. And then it gets to the return statement. Return statements are kind of puzzling in asynchronous methods. It looks suspicious, right? What are we returning? A variable of type storage file. What did we say that the method returned? Something of type task of storage file. And we've already returned it. We returned it at the first await point. So obviously, this return statement isn't going to be returning the task. That's already happened. It's been given back to my caller. Instead, in an asynchronous method, return has different meaning. Return, effectively, the way I think of it, is that task of storage file is the physical return type of the method, and storage file down here is the logical return type of the method. So the return type, the return statement is going to say to the internal plumbing of the future object that it created, it's going to say, okay, future object, you used to be in a state of not yet completed. Once we get to the return statement, I want you to transition into a state of completed with the following answer. And anyone who awaited with you, or anyone who signed up a Lambda as part of their continue with, I want you to trigger them to run at this point. So, at this point, when it gets to the return, it's going to trigger its caller to continue. Let's Control- to go back to the caller. And when that return statement happens, then the rest, the continuation of this method, will be triggered to run. So that, in a nutshell, is the control flow that happens with asynchronous methods. That's really good. Let's go into this definition, because I want to do a bit more work to it. We said, this is the 21st century, this is the internet. Failures are going to happen on machines completely outside my control. I need to make my code robust for errors. There are going to be network errors, there are going to be all sorts of errors. How am I going to do it? Well, where might it file? It might file inside OpenAsync, for instance. You remember in the picker, I could have picked files off SkyDrive or my local drive. Off SkyDrive, it could certainly have had a failure, especially if it was trying to use Wi-Fi inside a TechEd conference. Even off the disk, it could have failed if the file didn't exist anymore. Even file open picker might have failed, or set source async might have failed. Anything could have failed. And actually, the interesting thing is that a lot of these things, when we invoke an asynchronous API and we get something back immediately, most of the time, by the time we get this thing back, we don't know if it's going to succeed or not. We only know later, 5 seconds later, after it's done the timeout, whether or not it's going to succeed. So merely the act of invoking this API, pick single file async, getting back an iasync operation, most of the time this is going to succeed. It's only later on, when I await it, that at the time it failed, then the await operator will call the exception to be rethrown. Now, just like whenever you try to make a demo that depends on the internet working, it fails. Whenever you try to make a demo that depends on the internet not working, it succeeds. So I'm going to just invent an exception. Windows 8 tip. With the file open picker, if you fail to specify the file type, then it will fail with an exception. So I'm going to fail the specify file type, and it's going to throw an exception. It's going to throw an exception when the await resumes. And what happens with this await? Well, it just gets thrown inside this method. This is an asynchronous method. And by the time I discover I wish to throw a method, it's almost too late because I've already returned a task of storage file to my caller. But if my method has an exception that's unhandled, then instead of saying that this task object should transition into a I am completed state, instead it says I should complete into a transition into a failed state. What that means? We know what that means. It means that anyone who was awaiting for me, here, when they were waiting for me, when their await operator returns, they were awaiting a task, a future object that ended in a failed state. So when their await operator finished, then the exception will be rethrown. This is kind of squirrely. Let's just step through what's happened. I called pick single file async. I got back a future object, iasync operation, but then an exception happened, so that future object ended in a failed state. No exception was thrown yet. It was just an object that existed in memory that was marked as being in a particular state. Then, when I awaited it, it unwrapped that future object. It unwrapped the exception and it rethrew the exception. Then, because I'm inside an async method and I didn't handle the exception, then this throw an exception got wrapped back into the task that I had already created earlier. And then here with the await operator, it got unwrapped yet again. Well, it sounds complicated. It sounds like it's taking a little bit of overhead. It's not much overhead, not much extra overhead, and it's dwarfed by the rest of the overhead just for the normal .NET exception handling mechanism. You might worry, if you keep squirreling away exceptions and rethrowing them, squirreling them and rethrowing them, aren't you losing call stack information? The answer is, because that's what normally happens when you rethrow an exception. The answer is, no, that's not. We made a change in the .NET framework to allow us to store proper exception information when an exception gets rethrown, and we're using that for async operations. So I'm going to handle it, and I'm going to handle it in the way I know best, with a try statement. Try catch exception. Don't have much to do with it. Model.status text equals oops, an error. I did write oops, an error occurred, but then when I was practicing this talk, people pointed out to me, Lucian, you don't know how to spell the word occurred. So I thought I'd skip that for now. So let's run it. F5. I'm going to go here. Oops, an error occurred. That's because I'd commented out the filter type, so the file picker thing couldn't show. It threw the exception, got wrapped, rethrown, and this is where it ended up. So the exception handling is working exactly how I want it to. If any of you have tried doing exception handling with the callback and lambda style of asynchronous programming, you'll know that it's an absolute dog. You'll know that each exception handler has to be written twice, basically. Once in case it got thrown synchronously, once in case it got thrown asynchronously, and you can't use try catch blocks anymore. You have to use if statements to catch exceptions, which is the worst way of handling exceptions, right? An if statement to catch exceptions combines the worst of explicit error checking with the worst of exceptions. So it's really important that the async language feature makes asynchronous APIs compose. We already saw that it made it compose with semicolon. Now we see that it makes it compose with the try-catch combinator in the language. Well, where have we got to? Actually, there's a funny story about that. Streams, right? When you're doing stream.copy, if you want to copy from one stream to another, this method that's built into the .NET runtime. Since .NET 4, we wanted to have a version of it called copy async. Because even in .NET 4 times, they were making asynchronous APIs that were just a pain to use. And they were a pain to write, actually. And the team in the .NET framework who was charged with implementing copy async tried. But because copy async, obviously it's copying from one stream to another, it needs to have a while loop, it needs to handle exceptions properly, it probably buffers them or does something like that. It's hard to write in the old callback style of programming with lambdas. And indeed, when they got to 120 lines of code with the nested lambdas, it was very subtle code, it was macaroni code. It got to the point where the code reviewers on the team said, we do not have confidence that your implementation of copy async is correct, therefore we're not going to include copy async in the .NET 4 framework. Anyway, once the language feature was introduced, it got easier to implement. Now it's just down to 10 lines of code using await, and it's correct. And of course, the code reviewers gave the thumbs up and it passed. So now we have copy async in the framework because the await operator has made programming this stuff so much easier. Anyway, where have I got to? We've shown that the await operator made it compose better with the language things. Let me scroll down to here, and I'm going to uncomment this because I'm going to want my code to start working again. Var original file equals await picker.pickSingle file async. There's something else I can do with this. I'm going to factor it out, put the await statement on a next line. Original file operation equals picker.pickSingle file async, and var original file equals await original file operation. I haven't done any magic. It's just an expression like any other expression. I can use it wherever I want. I can invoke an asynchronous API, but I don't have to await it immediately. And there's a really good reason why I might not want to await it immediately. Watch this. Well, what was this code doing? It was awaiting you. Actually, I don't want to put it here because that's kind of pointless. I'm going to put it all the way up here where I can do something much better with it. I just call it original file task. That's a naming pattern I use. I guess it's Hungarian notation, suffix notation, so you might not like it, but it makes it easier for me to keep track of. Original file task was the task of storage file, and I get back. So the reason I'm doing it here is because I'm hovering over it to see where am I using it next. I'm not using it until way down later. And I'm doing a whole bunch of work in the meantime, a whole bunch of work to download stuff off Flickr to get the images. And you think, I don't need to do that. It's like the police officer says when he pulls you over to speeding and you say, but I had to get there urgently. He says, well, if you wanted to get there early, the best way to do that is to leave earlier. Yeah, thanks. Still gives me the ticket. But what I'm going to do is kick off this downloading from Flickr, because that's going to take a long time. That's going to happen while the user is on the picker choosing what image they want. And only later on, when I actually need the result of the picker, only then am I going to await it. And the crucial thing here is that I'm doing two things at the same time, right? I'm doing the file picker, and that's working, and that's staying responsive. Meanwhile, I'm downloading stuff from Flickr, and there are no background threads involved here. I'm not using background thread worker. I am not using task.factory.startNew. I'm not using any extra threads. All of this work is still happening on the UI thread. It's just happening on the UI thread smarter, interleaving the various bits of work. Because remember back from the original slide, the amount of work we're doing is this tiny, tiny capsule, like 1 millisecond in order to send a network request. 2 milliseconds to handle it. That is not going to hurt user responsiveness. So I don't even need to go to the work of background threads. I could do it all on the user interface thread as long as I don't block it and I share it responsibly. And that actually is exactly the same message we have for using Azure or doing any kind of server programming. If you use your threads responsibly, then you get much better resource usage out of them. Well, let's run it. Let's just see that what I said is happening. I'm going to do flower, pick the image, pick this one. I'm taking time, and in the time I'm taking, it is going to Flickr. It is downloading 100 images off Flickr. And so that's why it said calculating mosaic instantly. There was no time interval when it said downloading images. It just did them straight away. That's great. I've improved user interface responsiveness without having to optimize my algorithms, without having to do anything apart from kick off the asynchronous operations earlier and use them at a time when I needed them. And just like I've done there, let's go back here and put this. Just like I did that with the task thing, I can do exactly the same thing. With Windows Runtime Async operation types, no difference. I can await them just the same. I can separate the kickoff from the awaiting. Actually, there's no point here, is it? Because if I click over this, we see it's needed on exactly the next line. So I haven't bought anything here. But maybe if I wanted to, I could have await task.delay of, if I wanted to do some kind of very important work here, takes 5 seconds, I could have separated that as well. Just to say, this new task.delay API, I didn't use thread.sleep. I totally did not want to use thread.sleep. Remember, I'm still on the UI thread. Nothing I've done has created a background thread. The async modifier does not create a background thread, so I am still on the user interface thread. If I did thread.sleep here, the UI thread would be blocked for 5 seconds. So await task.delay is like a cooperative version of thread.sleep. It's saying, yield this thread back to the caller, to the XAML message loop, and schedule my continuation to run after 5 seconds. Actually, let's make it a bit longer. Make it 8 seconds. And I'm going to set a breakpoint here. And let's just step through the code to see exactly what happens. We're going to run it. I click this. Now it invokes the choose image async. It hasn't shown me the picker yet. Why hasn't it shown me the picker yet? Because my UI thread is currently at this breakpoint. My UI thread has not been given the chance to pop up the picker. So I'm going to do step over. And now the UI thread... I was going to say that UI thread is showing the picker right now, but it... I know it's not. Sorry, I'm just brain mistake. I kicked this off, but I haven't yet done an await statement, have I? So it hasn't yet been able to return control to the UI thread. So it hasn't yet been able to pop up the picker. But as soon as I execute this await statement, then the UI thread gets to run. Then the UI thread can do this picker. And you can see it's responsive while I'm waiting. But I hadn't yet picked anything. But 8 seconds later, on the UI thread, the continuation of this method was scheduled to run because the task.delay had finished. Isn't that neat? How control, even though it was on the UI thread, switched back here. And if I try to look at what the UI thread's doing, now it's blocked because now the UI thread has returned to this method. So now I have to return back to my caller to finish this operation, await. And once I've done that, then it gets back to its responsiveness. Implicit parallelization. I did parallelization, not with anything fancy, but just with the await statement moved to a different place in my code. And you might have picked up something else really important about this style of coding. If I had started doing some CPU-intensive work here, I would have blocked the UI thread. I don't want to do that. So whenever you're using asynchronous methods on the UI thread, avoid CPU-intensive work. We've seen, let's just delete that actually, because I don't want to continue with that. We've seen two different types, the Windows Runtime Future Async operation and the .NET Future, the task of T-type. And you're saying, well, they both behave in pretty similar ways. Why don't they just do the same type? The answer is Windows needed to make a future type that could be consumable by JavaScript, by C++, and by .NET. So they couldn't use the .NET task type. And .NET already had a vast infrastructure around the task type. They introduced with the task parallel library and TPL in .NET 4. So .NET really wanted to stick with task type. Well, given that we've got two separate types, can we convert between them? The answer is yes. If I do .asTask extension method, that will convert my async operation into a task. So now the thing I've got here, I should change the variable name, it's now a task of tResult. So it's very easy to convert from an async operation to a task, and we'll see a couple of ways where that's important. So where have we got to? What we've seen is some really important things. We've seen the await operator makes the rest of your method a callback, avoiding you from lambda callback hell. You've now got a good, clean way of programming against asynchronous APIs. And that has put C# and VB into the premier spot for programming any kind of asynchronous APIs. The next thing we saw is the async modifier. If ever you want to use the await inside your method, you have to put the async modifier on the method, just so the compiler knows to put all that plumbing. A phrase we use is makes the method asynchronous. That's not the same as saying makes the method run on a background thread, because it doesn't. It just makes it asynchronous, meaning it returns a future object. We're not saying how it returns a future object. That's done by the plumbing. It returns a future object. And what we've seen are awaitables. We've seen on the .NET side the task or task of T awaitables. On the .NET, the async action or async operation awaitables. Some of them return from .NET APIs. The others return from Windows APIs. You can await them directly. You can await them multiple times. You can store them, as we saw, and we can await them later if we needed. And you can convert the async operation into a as task and await it later if you wanted to do that for whatever reason. You might ask, well, can we convert a task into an async operation? Yes, you can. There's an API for doing that. It's not as clean as task. It requires passing the an async lambda or an async delegate, but it's still just 3 lines of code rather than half a line of code. And while we saw something, I didn't stress the point earlier, but I do want to stress it now, is we saw 2 different types of method. We saw task returning async methods, which return this future object, and we saw void returning methods like the event handler. I mean, an event handler is always void returning. XAML, it gets the click, it fires off your event handler, but XAML totally does it in a fire and forget way. It just launches your async operation. It doesn't care when it finishes, so it doesn't care about getting a future back. All it needs is a void back. And so void, the time to use void is only for firing forget things like event handlers, for starting independent flows. But when you return future types, task or task of T, those can be awaited. The caller is able to await them. And generally, in your code, whenever you're writing asynchronous methods, they should always be task returning unless they're event handlers or event-like things, in which case they can be void returning. Yeah, that's a small sentence now. It's a really big point. We see lots of people making bugs with it. If someone asks me, what's the #1 bug that coders make when using async? It's writing void returning when they had to have been writing task returning. And if you go to tomorrow's async talk, the first third of it is about ways to recognize where void returning is happening and looking at the patterns to make task returning a reality. So let's go back to some code at this stage. Where have we got to? We saw that we got back task objects, we saw how to use them, and we saw that we could say var choose images task equals something Where are we? Var original file task equals choose image async. We saw that we could get back a task and use it later. This is what I was talking about, a first-class object. This task is the object in memory that we can dot off and we can do things with. And I said that there's a whole .NET part of the .NET framework built around methods on task and things we can do with them and ways to create them. And there's also one part I talked about, which was we had to avoid doing CPU-intensive work on the UI thread. Let's suppose I haven't actually done profiling, and I should always do profiling before I do anything, but for the sake of this demo, let's suppose that parse photos from XML was a CPU-bound piece of work. Maybe Flickr returned to me 500 K's worth of XML, and it takes me serious time to convert it into an X document and walk it. Then, if I had this here, this would be doing CPU-bound work on the UI thread. I should have said something that's really important about the await operator. Await. You get given an async operation or a task, you do await on it, and no matter where that piece of work's happening, could be on the UI thread if it's an async method, it could be on a background thread if someone implemented it that way. It could be on a different computer halfway across the world if it was a network download. That work is happening somewhere. But when I return from the async method, because I used the await operator, then the rest of my code is going to continue on the same UI context where it left off. It's going to continue on the UI thread. So I'm clearly back on the UI thread now, and if this took too long, I can't do this on the UI thread. So I want to push on a background thread. And there's a new API to do it. Await task.run. Give it a delegate. What does that line of code mean? It means I had some CPU-bound work. I had a whole bunch of code here. I had like 6 lines of code. Most of them were just doing orchestration, we call it, or choreography, saying start this download, finish this download, update the UI in the following way. All of those were taking milliseconds. None of those were important to push on the background thread. In fact, it was easier if they stay on the UI thread. Why? Because if they're on the UI thread, I don't need to worry about thread-safe access to my variables. I don't need to worry about race conditions. I don't need to worry about mutexes. I don't need to worry about the fact that in a XAML program, I can only update the UI from a UI thread. Like you have to use dispatcher.beginInvoke everywhere. I don't have to worry about any of that. That's why I want to keep the bulk of my code that's just doing small orchestration on the UI thread. I'm only going to put that tiny nugget of CPU-intensive work on the background thread. And usually what we find is that tiny nugget is really simple. It doesn't need to interact with the UI in detailed ways. It just does its own piece of work and returns something. And task.run takes a Lambda. It schedules this Lambda to run on the thread pool. When the thread pool has time, it runs the Lambda, and when the thread pool, and remember, task.run, what does it do? Task.run is returning me a task of ilist of photo info. So it's returning me a future object. Once the thread pool has finished with executing that Lambda, then the task is marked as completed, so my code can continue. So what you've seen with task.run is a radically easier alternative to using thread.startNew, a radically easier alternative to using background thread worker. We can do more with it, of course. If I wanted, I could have done a curly brace here and had a proper statement Lambda rather than just an expression Lambda. It's a very easy way to schedule work to run on the background thread. Actually, let's just do that. Turning it into a statement Lambda. I'm scheduling some work to run on the thread pool. And remember what I said about server scalability, that it's important not to tie up the thread pool too much because it's a limited resource. Normally on the client, you don't worry so much because there aren't many apps running and you can use the thread pool more. But that's not always true. We found when we're building the next generation of VB and C# compilers that we were using asynchronous APIs all over the place. We were using the thread pool a lot. And the thread pool, let's suppose I'd done something like thread.sleep of 5,000 here. The thread pool, if it discovers that all of its threads are exhausted in its pool and more work has been scheduled, say using task.run or any other mechanism, then it will create a new thread, a new resource to run that new work. But it has what we call a hill climbing algorithm. So only if, you could schedule new work, but if you're using threads on the thread pool pointlessly, then the hill climbing algorithm comes into effect. And the hill climbing algorithm does things a bit slower. It just ramps up gradually to make sure, it doesn't fire off and create 500 threads instantly, because that would be pointless. Most of the time, for optimal performance, you only actually need as many threads as you have CPU cores. So it never wants to create lots of them quickly. So if I was wasting threads by tying them up here with a blocking operation, I could conceivably be starving someone else who was trying to use a thread pool. That would be bad. So really, I'd want to use await task.delay of 5,000. So I can use await inside my lambdas. Actually, if you look at this, it says you can't use await inside your lambdas. Hover over it. Error. The await operator can only be used within an async lambda expression. That's obvious. Just in a normal method, we needed the async modifier to have the compiler generate all the plumbing to allow us to use await. So, I can use the async modifier inside my lambda to allow the lambda to do all of the plumbing, so it can use awaits too. Let's just delete all of that, because that was an interesting sidetrack on thread pool usage. Now let's get somewhere else. Oops. Let's do something else. Let's look at create mosaic. When I ran this program, it was creation of the mosaic that was taking the longest time. And I'm going to show you another piece of magic we can do with it. What I'm going to do is another of the important combinators we can do in the .NET task library. So I did this, let's call it var mosaic task equals mosaic builder.create mosaic async task. If it's taking 15, 20 seconds and the user doesn't know that it's working, they're going to be a bit worried. So what I'm going to do is say, after it's been running for 3 seconds, let's pop up some text and say, still working, just so that users know it's working. And you might laugh, but that's a really common pattern we see elsewhere. Like if a Windows 8 or Windows Phone application is doing a sync, if the sync finished immediately, it doesn't bother changing the UI. But if the sync is starting to take longer than half a second, then it can show the UI. It can show syncing at the top to show you that something's taking some time. So let's put a delay, var delay task, task.delay of 3,000. I'm not going to await it, actually. I'm just going to start the timer going on this one. And then I'm going to say var winning task equals await task.when any of mosaic task and delay task. What that's saying is I've got 2 tasks in flight at the moment. When I say in flight, remember, they're not using background threads. They're both using the UI thread or scheduling in some other way. But I'm going to see which of the 2 of them finish first, and then winning task is going to tell me which of the two tasks finished first. If winning task equals delay task, then model.status text equals still calculating. Isn't that great? When any is such a powerful combinator. I could have factored this into my own separate library if I wanted to write a general purpose library for popping up UI if something takes too long. You know that in Visual Studio. If an operation takes longer than, I think, half a second, then it pops up a dialog that says operation still in progress. So very general purpose thing. We could factor it out into a general purpose library. The reason we can factor it out is that we have now these task objects, these future objects, as first-class citizens. First-class citizen means it's an object, you can dot over it. Just as IEnumerable open up the whole world of link, open up a whole world of combinators and library functions that anyone could write on top of IEnumerables, no matter where they came from. So the task type opens up a whole world of combinators that can operate upon futures no matter where they come from. And that's why the as task is useful. So after this, we still need to say var mosaic equals await mosaic task. And we'll run it. Pick something, some image, calculating mosaic, still calculating. Yeah, it worked. So what have we seen there? Task lets you coordinate activities. Task opens the door to a whole world of task combinators. Here I've written some of them. Await task.delay, we've seen already. That returns a task. We'll schedule its continuation to run after a bit. Await task.yield. What does that do? That's a good question. What happened is that we realized towards the end of Visual Studio 2012 that what await task.yield did was pretty much unpredictable. It varied quite a lot depending if you were using it on WPF or Silverlight or ASP.NET or Windows 8 or Windows Phone. There wasn't a consistent story around it. So our guidance is don't use await task.yield. If you can't answer what exactly it does in unambiguous terms, then don't answer it. And I can't tell you what it does, so I'm not going to use it. We saw task.run, another combinator to give you back a task. We saw await task.whenAny. It returns the winning task out of an IEnumerable or an array of tasks or a params array of tasks that you give it. Await task.whenAll will finish when all of the tasks are finished. And if all of the tasks, say all of them were task of int, task of int, task of int, if all of them were task of the same type, then what you get out of it will be an array of integer, giving you back every single task that had finished. How much time? I've got 7 minutes left, and that is just enough to show you cancellation. Cancellation is important. Like whenever we have long-running internet operations, the user needs to be able to cancel them, otherwise they get frustrated. How are we going to do this? Well, create mosaic async. Let's say that's the one that takes a long time. There's an overload of it which takes an optional parameter which is a cancellation token, and that's how we're going to do cancellation. I'm going to write the code to do it and then we'll fill it in. We're going to have cancellation token source CTS equals null. Oh, I'm sorry. Thank you about that. So let's go back. I said this was the long-running task. It takes an optional parameter, which is a cancellation token. That's how we're going to do cancellation in .NET. So we're going to do it here. And the first step is cancellation token source equals cts.null. I'm going to write some lines of code that look incomprehensible at the moment, but they'll make sense. CTS equals new cancellation token source. Cancellation token source is what will generate cancellation tokens. Later on down here, I can pass the cts.token. And afterwards, I'm going to set it back to cts equals null. What's the difference between cancellation token source and cancellation token? Well, cancellation token is like a light bulb that anyone can look at. If the light bulb is switched on, they say, aha, someone has requested cancellation to happen. Cancellation token source is like the light switch, which can cause, which can indicate, which can change the light bulb. It can turn on the light bulb. We had to separate them because we're going to tell hundreds of APIs within our code that cancellation has been requested. We want to give them the power to look at the light bulb, but we don't want to give them the power to toggle the switch. Only the user can toggle the switch. So we give them cancellation token so they can look at the light bulb. We will keep the cancellation token source so we can operate upon it. And what I'm going to do is inside go back. When the user hits the back button, that will be a good time. If CTS is null, return. Otherwise, trigger cancellation. So, if the user tries to go back, then it will signal the cancellation token as the light bulb to show that cancellation has been requested. And that's how it will work. And if I run it, I won't run it yet. If cancellation has been requested, inside create mosaic async, let's say, if cancellation had been requested, then create mosaic async will finish as soon as it looks at the light bulb, and a task that was returned in mosaic task will finish in a particular state. It won't finish in the completed state, it will finish in the cancelled state. In other words, it will finish in the failed state with an operation cancelled exception in it. So anyone who tries to await it, because it's a cancelled task, they will end up rethrowing that operation cancelled exception. So if I want to catch cancellation, I do it in exactly the same way as I catch exceptions normally. Catch operation cancelled exception model.status text equals cancelled. If I run this now, I select this, pick an image, oh, not from SkyDrive. If I try to go back, request cancellation, throws the exception, and I caught it just fine. The final thing I want to tell you in this talk is this. Let's suppose pick single file async. Actually, that's a bad example, because if the user is inside the full screen picker, then they can't click the back button to cancel a thing. They can't do the other UI affordance. Let's try inside open async. If that one finished, I should have made this method take a cancellation token cancel equals default of cancellation token. So I'll put an optional parameter so that this API can take the cancellation token as well, like the other built-in APIs. I can do this default trick because cancellation token is a struct. So default is just the default structure of that type. I'd like this open async, it might take time, to take the cancel token, but there isn't an overload which takes that. And that's because the Windows API does not use cancellation in the same way. What I have to do instead, .off it, you can see the way Windows API does cancellation is it's got a cancel method on it. Cancel method. What that means is that if the light bulb goes off, if I'm using this idiom of cancellation, that is, invoking cancel explicitly on an ongoing task, then I have to do bookkeeping. I have to do bookkeeping to keep track of which is the current task that's ongoing, so that when I'm looking at the light bulb, I can look up my book list to see which is the task that's in flight, and I can cancel it. That's a pain. I don't want to have to do that. I much prefer the .NET style of cancellation, which just has this light bulb. I pass it to APIs, and the APIs look at it, and that is where the beauty of AsTask comes in. That's one of the beauties, is that I can pass the cancellation token to it. So any .NET API that you can cancel that returns an async operation or an async action has .AsTask on it, which also takes a cancellation token. And that is how we bridge from the Windows runtime world into the .NET runtime world. So those are the two reasons we have for using AsTask. One is to turn it into a task, so we can use the .NET library of combinators, task.winAll, task.winAny. The other reason is so we can pass a cancellation token on it. Where have we got to with that? Cancellation. We said, normally with task.run, we said there's just this small nugget of CPU-bound work that wanted to do its stuff and then gives an answer at the end. But there are also going to be places where we kick off a long-running async operation, and we want to interact with that long-running async operation while it's in flight. And the two ways we want to interact with it are, we might want to cancel it, or we might want to see where progress is done with it, and that is where we're going to use either pass in .NET APIs, pass cancel or progress if it supports those things, or for .NET Windows runtime, we do AsTask. Windows 8 has taken a huge bet on asynchronous APIs. If you had to program them with the callback style, it would have been a pain. The asynchronous support in the language makes this easier. And what we have delivered with Visual Studio 2012, with the new versions of C# and VB, is we have made the Windows 8 bet justified. We have made asynchronous APIs there and across the Live SDK and across the Azure SDKs. We've made all of these asynchronous operations easy to use. Thank you.